When you implement a linked list, then each element of the linked list needs to have a value and then a reference to the next thing in the list, which will be similarly represented. An int list written with this declaration will not work, however. The problem is that we need to, in memory, have space for v, right? That's 4 bytes, that's no problem. And then we need to have space for a struct int list. Well, a struct int list needs space for a v, and then it needs space for an int list, which needs space for a v, and so on. So this struct declaration will be rejected by the compiler because it doesn't correspond to a fixed amount of memory. It's an unbounded amount of memory. The way to implement a linked list is that we need to make next a pointer to the next node in the list. And now we have a struct that needs room for v, 4 bytes for v, and then 8 bytes for next. And this is a sensible struct declaration from the C compiler's perspective because it knows how to lay it out in memory. Next will be an address, that is, it'll be a pointer to some other record that has the same shape, has a v, and has a next. And the way we terminate the linked list is by using a special value null, which is just 0, but we write it as null by convention to highlight that it's the 0 pointer. Here's a similar kind of linked list called rec that has a next pointer. In this one we have an array of 3 integers in each node followed by another integer. And we're going to look at a function setVal that takes a record and a value, and it's going to walk down the linked list represented by that record, and at each node it's going to set a at position I to be the given value. If you think about the layout of this record in memory, it's going to have room for the array a, that's 3 integers or 12 bytes. It's going to have 4 bytes for I, and then it's going to have the last 8 bytes for next. That'll make it 24 bytes, and everything is aligned, as it turns out, without any padding. We can think of this A as being A0, A1, and A2. So as we look at the machine code, it may be helpful to look at things that way. Next, recall, is going to be a pointer off into some other record, or a 0. The loop terminates when we get to an R next that was null to terminate the linked list. Here's the machine code we get by compiling this program, looking, well, just at the inner loop, but that's mostly everything. So RDI comes in as the argument R. ESI is the argument val. ESI instead of RSI because it is an integer. So when we're in this loop, what we do is move SLQ. So that means we need to take something that was an integer and make it long-sized because we're going to do some pointer arithmetic. So that kind of thing happens when you're taking an integer and using it as an array index, right? So it seems likely that we're computing the I offset of A here. And where does I come from? It comes out of the record. So that's why we take RDI, which is R, and look 12 bytes into it to get 4 bytes that we sign extend out to 8 bytes. So that's RDI plus 12 gets us the I field. So that's what that first thing is doing. It's getting the I field as the local variable I is the I field out of R. And that's in RAX. So we're taking RAX, multiplying by 4, and adding that to RDI. So that's doing the array index within R. Since the array starts at the beginning of a record, then we can use R as equivalently the pointer to this array. And so we're setting val, ESI as val. We're putting val into the array at that position. Finally, we need to do R next and move that into R. So that's what you see here. We take RDI plus 16. That gives us the next field, and move that into RDI. So we replace R with R next. We make sure that it's not null, and if so, go back around the loop.